So yeah, hello everyone. My name is Antonio. I'm a doctorate candidate at the University of São Paulo, and I'm happy to be the first to talk here at the Speaker's Corner. I will present a recent work of us about correlations in buckled graphene. But since I'm not really sure how many of you are familiar with graphene and gauge fields in graphene and electronic interactions, I'll give you an overview, a theoretical overview about it, and then I will actually discuss about our work. So first of all, you may be wondering if graphene is magnetic or not, since if graphene has any correlations, if I'm talking about correlations. And specifically, I'll be talking about magnetic correlations. So the question that comes first is that if freestanding graphene is actually magnetic or not. And there is a thumb rule we can think for graphene, so which is known as the standard criterion. Which tells us if the product of the density of states at the Fermi level multiplied by the electronic interactions like hopping, some sort of coupling constant is larger than 1, then we should expect some sort of magnetic ordering. But it turns out, sorry about that noise, is a building nearby. But for graphene, it turns out that there is no magnetic ground state, and the reason for it is that if you look at the density of states of freestanding graphene, deep in the bulk, the density of states should be 0, close to the Fermi level. So there is no room for electronic instabilities. But when we add any sort of gauge field in graphene, so for example, if we consider graphene at the quantum Hall state, we'll see that the presence of gauge fields actually provides this Landau quantization. By the way, can you see my mouse here?
Oh. Yeah, works well.
Okay. So in the presence of gauge fields, we actually have this Landau quantization, and right at the Fermi level, we see there is one Fermi level, one Landau level lying exactly at the Fermi level, which is actually a feature of graphene's Dirac dispersion. And then we might indeed have some room for electronic instabilities. And there is actually several examples where we can see that. So maybe the simplest one is actually graphene at the quantum Hall state. We see that in the presence of an orbital magnetic field, graphene actually has an antiferromagnetic ground state. But this is only with the orbital component. Actually, if you apply a magnetic field, you actually end up with a Zeeman component. And the situation, the real situation is actually something that has this extra Zeeman field that will try to align those these spins to the same direction, and you end up with this canted antiferromagnetic order for general systems. Another example where we have magnetic orderings in graphene is when we consider strained graphene. In this case, we actually can, I will enter in more details later on, because this is exactly what we are exploring in this work. But straining graphene, you can actually translate as some sort of gauge field. And it was also predicted that strained graphene also supports a magnetic ordering. It turns out to be a ferrimagnetic ordering. And even for a twisted bilayer graphene at small angles, you can translate the coupling between the two graphene layers as some sort of gauge field. It was also predicted that these flat bands formed because of this Landau quantization actually possesses a magnetic ordering. So let me go a bit into more details on strained graphene. So if we think about a tight binding model for graphene, actually the C3 rotation symmetry with respect to any atom here in the crystal structure will make you believe that those three hopping constants are the same. But if you strain graphene, for example, with a unaxial strain field, you will break this C3 rotation symmetry, and then there is no reason for you to believe that those three hopping constants are equal anymore. And if you make small changes in them and look at the low energy limit of this theory, you'll see that the Hamiltonian actually acquires an extra term besides you have this linear charming momentum that graphene, even freestanding graphene has, but you also have now this extra term that looks like a gauge field, but this is a gauge field that changes in sign depending on the Valley number. And of course, that's required for you to have this sign dependence with the values, because otherwise you would break time reversal symmetry. And you can actually relate the hopping constant with this gauge field, but with those two expressions here. So if you somehow modulate your hopping constants in any way, you can actually end up with some effective pseudo-magnetic field. So let me now emphasize some difference between Landau levels coming from electromagnetic fields and Landau levels coming from pseudo-magnetic fields due to strain. And so for electromagnetic fields, the zeroth Landau level, the Landau level lying at the Fermi energy, actually has the strong sublattice to valley locking. So which means that if you have your wave functions lying in one of the sublattices, they will be strongly valley polarized. And what happens then if we turn on the interactions? Well, Lieb's theorem, since those two sublattices will be equally populated, Lieb's theorem tells us that there is an antiferromagnetic ground state, which is exactly what I just discussed with you, besides those extra Zeeman terms that I told you. So if you introduce, of course, the extra Zeeman field, you end up with the canted antiferromagnetic ground state. On the other hand, if you have strained graphene with these axial gauge fields, you no longer have these sublattice to valley locking. You actually have a strong sublattice polarization, but there is no valley polarization going on here. You only have your wave functions strongly localized close to one of the sublattices. And what happens with interactions then? Well, you could think that now we have a competition of this sublattice polarization with something that Lieb's theorem would try to force the system to an antiferromagnetic ground state, and we actually end up with a ferrimagnetic order in this situation right here, which is also a result that I just showed you. So before I actually start telling you about our work, let me tell you about the experimental motivation for what we did. And this is actually this was actually a paper from Eva Andre's group showing that you have in some graphene samples you have those reeds, and those reeds actually introduce a lot of in-plane strain in graphene. It turns out that when these the structure relaxes with this in-plane strain, it actually acquires a buckling pattern. So you can see the two reeds right here, and deep inside this region here, if you zoom in, you can actually see this buckling pattern that actually forms some sort of triangular lattice. If you do a bit more, a couple more things here, if you when they try to do scanning tunneling spectroscopy, you can see the topography of the sample in this buckled region. If you measure the spectra right at the crest, at one of those crests here, you can actually see Landau quantization. And if you compare the crest with the valleys, you see they have opposite sublattice polarization, which somehow tells you that the effective pseudomagnetic field is changing sign when you go from a crest region to those valley regions here. Right, so let me now actually present my work for you. This is a work I did in collaboration with Jose Lado at Aalto University and Eduardo Durval and Gabriele, which are from the three of them are at the University of São Paulo. So I'll quickly present the model for you, discuss about the ferrimagnetic ground state, and tell you how this system behaves with charge doping and compare with some experimental data. Finally, I will end up showing you how to electrically control the magnetism in this system and tell a bit of about the spin orbit effects in this very system. So the model is then quite simple. It's just a matter of considering the STS data. It is just a pseudo-magnetic field that has this superlattice pattern here. This period here is much larger than the graphene lattice constant. Is something about 14 nanometers. And it forms this triangular pattern here that we modulate, that we try to bring up with this effective magnetic field. So what you are actually looking at here is the Valley-Berry curvature of this system. So it is also showing you that you have some sort of valley polarization here when you compare crests with valleys of this system. And well, then this will of course bring some sort of bring to the table some sort of Landau physics. And the first thing that we do then is to compute the Venn diagram of the system. You can actually see that the energy scale here is much smaller than the hopping constant, and the band that is lying closer to the Fermi level is actually the band that we call the zeroth Landau band. You see some things going on here. So since this energy scale is much smaller than the hopping constant, you actually have a very small bandwidth. And you could think that if you add electronic interactions in this system, then these electronic interactions, even for graphene, would be much larger than this bandwidth of this system with Landau quantization. Another thing you can see here is that actually Valley number is a good quantum number, which is some sort of heritage of the pseudo-magnetic field that I introduced, since I just showed you that the Valley-Berry curvature actually changed in sign here. We actually have this same sort of physics presented here in the Venn diagram, where we see strong valley polarization. And then for our calculations, we try to be conservative here. We consider a Hubbard constant equal to the hopping constant. this is actually smaller than the critical value for graphene, because even though I told you that Stirner's criterion tells you that graphene should not be magnetic anyway, if you keep increasing and increasing the coupling constant, of course, there will be a moment when you do have electronic magnetic ground state, or a correlated ground state at least, even though the density of state at the Fermi energy is 0. So, and this value turns out to be 2.2 times the Hawking constant. So the first thing I have to tell you is that the FT estimations actually say the Hilbert constant in graphene is smaller than that, so something around 1.8 times the Hawking constant, if I remember well. But we try to be even more conservative and use values smaller than the DFT predictions, just to make sure that any ground state we see here is robust enough to any possible changes in the Hilbert constant. So, well, we can actually see that the local density of states look like the experiment, which is nice. And when we turn on these electronic interactions, what we see is that first we have a correlation gap opening in the system. And if we look at the magnetization of the system, we actually see this this modulated pattern. So you can actually think of this pattern as some sort of honeycomb superlattice, where you have two different sublattices with different magnetization. So it's some sort of antiferromagnetic honeycomb superlattice that we actually see here. One remark that I will make here is that this is not a perfect ferromagnetic region, and even also this one is not a perfect ferromagnetic region. They both are ferrimagnetic instead, and this is in agreement with the discussion I just presented to you at what to expect when you turn on electronic interactions in strained graphene. So now we do have this modulated ferrimagnetism that organizes inside of a honeycomb superlattice, and we actually learned a bit more of this system as we investigated what happens when we tweak a bit the parameters of this system. So let me explain you a bit about other results in this experimental work that I just presented you previously. Something that happens when you try to gate the Fermi energy closer to the zeroth Landau level, or when you go away from the zeroth Landau level, what you actually see is that when you are lying with your Fermi level at this zeroth Landau level, there is a correlation gap, and when the Fermi level is gated away from this zeroth Landau level, this correlation gap closes. So this is also something we can see with our theory. So this is some results showing you what happens when we charge dope the system. So as I just showed you, we start with a correlation gap when the Fermi level is lying exactly at the at charge neutrality. But as we dope the system away from charge neutrality, we actually see that this correlation gap closes, as you see right here. So this is also in nice agreement with the experiment. And now what can we learn also by considering this ground state as a honeycomb superlattice? There's something cool that we learned we can make here. So we do have this localized wave functions, and remember that there is a buckling pattern right here. So if we introduce an out-of-plane displacement field, what happens is that this buckling pattern will actually modulate the on-site energies with the same functional form of the magnetic field. So you should expect this modulation to be to have higher amplitude here in this near these and these regions, but with opposite signs. And I can actually simplify this analysis by telling you that you can actually view the system as some sort of superlattice honeycomb. So consider now that you take the wave functions localized near these encircled regions as some sort of linear wave functions, and you then end up with this honeycomb structure, as I just told you. And if you translate this modulation of the on-site energy to this linear model, it actually means that you end up with a sublattice imbalance with in this model. It's actually not a symmetric sublattice imbalance. You see that the amplitude in one of the sublattices is higher than the other. So for 1 second, forget about any effects of electronic interactions. Let's go back to the system with no electronic interactions at all. So here we have no, the Hubbard constant is set to 0. So but still, if we apply this, if we add this out of plane displacement field, we actually see a gap opening, which is in agreement of with this idea of having a sort of Semenov mass that will gaps the system because it will break inversion symmetry of the system. And you can actually see that one of the bands are a bit further away if we compare with the other one, which is translating these two relations here. So this band is twice as distant to the firm level when you compare to this one in the bottom. Right, so now let's try to think what happens when we turn on electronic interactions. And there's a there's a simple way to think about it. So if we start here in the left with an antiferromagnetic ordering, and we keep increasing a sublattice imbalance term, we actually see that there will be this kind of splitting right here, and there is a point where actually we don't have an antiferromagnetic ordering anymore, but we actually have no magnetization at all in the system. We do have we end up with a strong sublattice polarization, but the net value of magnetization will be at least close to 0. That's actually something we can see with the full model. So if we now come back to the actual superlattice with the atomic limit and not anymore considering the veneer model, we actually see that as we so those are two order parameters that we defined for the system. I think this is the easiest to follow. This is the Niel order parameter of the system. And we see that as we increase and decrease, when we put both positive and negative perpendicular displacement field, we actually destroy the magnetic ordering, which is basically a translation of this idea that I just showed you. Right, so finally, let me discuss a bit with you what happens when we add spin-orb coupling. And the motivation for that is that these buckling patterns, I don't think I actually emphasized that, but these buckling patterns were obtained in both with graphene over niobium diselenide and with graphene over boron nitride. And it turns out that some DFT calculations show that when you put graphene on top of niobium diselenide, it has a Rashba-like spin-orb coupling, which is something between 20 and 40 milli-electron volt, depending on the edge physics of this graphene that you put over the system. So we actually added a spin-orb coupling above that order of magnitude. And when we look, so what you're looking at right here, let me just come back, is you are looking exactly at those two circles here, those two black circles. And you can actually see that you now have non-collinear magnetism in graphene. These values are actually not really high. They are much smaller than the out-of-plane component. So in principle, you should not expect to have a strong non-collinear component. But I also have to emphasize something else. This is the contribution that comes only from proximity with niobium diselenide. But since we have buckled graphene, we actually have a bit of sp3 hybridization as well, which brings an extra spin-orb component. So we have no estimation about that, but we can actually expect that these in-plane components will be a bit higher than what we calculated here. Here we have like 10 times, the in-plane components are something like 10 times smaller than the out-of-plane components. Well, that's pretty much what I want to present to you today. Let me just summarize what we have. So as you can see, there is an effective antiferromagnetics honeycomb superlattice in buckled graphene. It turns out that we can actually tune this system with an out-of-plane displacement field, and we can actually control magnetism with electric fields here. There is a non-collinear magnetic component if you turn on spin-orb coupling. And finally, something that I think is pretty cool is that since one of these substrates where these samples were prepared was niobium diselenide with superconducting material, there is plenty of room to study the interplay of this superlattice non-collinear magnetism with superconductivity here. And finally, let me acknowledge funding. And that's all I have to tell you. Please, if you have any questions, let me know. Yeah. Let me, okay.
May I ask a question?
Yeah,
Thanks,
sure.
Antonio. Let me try to understand. So first of all, I'd like to understand better the initial band structure. You're saying that the mini bands in the superlattice have a bandwidth of about 0.02 hop times the hopping strength.
Yeah.
And which is, I think, about 10 times smaller than the expected value of the next nearest neighbor hopping. So I'm wondering whether the effects associated with the next nearest neighbor hopping and with its, in particular with its position dependence, would potentially change the results.
Okay, that's something I don't know exactly how to answer you because we haven't considered any next nearest neighbors hopping. That's actually a good point. Especially if we think about any sort of spin-orb component or things like that. And also, I think that will be even more important than that, because this value here for bandwidth is actually overestimated because we rescale the system. So this is actually not the bandwidth for the real dimensions. They will probably the bandwidth will be even smaller, but I honestly have no idea how things will behave if we had nearest neighbors hopping here.
Yeah. Okay. Okay. If it's a rescaled unit cell, then also the next nearest neighbor hopping also increases with because near k points it's some higher order of momentum.
Yeah.
All right, and so also to understand, let me see. So what is the magnitude of the polarization of each orbital here, like roughly?
Yeah, so this is also something that was a bit tricky to actually give a quantitative estimation, because we rescaled the unit cell to actually compute stuff, and then we have about some tenths of bar magnetism for by unit cell, but I'm not really sure if I can really give you an exact number here because of the rescaling. I wouldn't trust on quantitative results here, much more on qualitative stuff.
Oh, so you did not rescale the electron-electron interaction here?
No, I just set them to be equal to the hopping constant, yes.
All right. Okay, thanks.
Yeah, sure.